Yeah. All those girls. Your mic is on.
Hello.
Hi.
So why are we so few? Only 57 have logged in. Is there a communication issue? Okay, I think we will need to start. We don't have to wait for them indefinitely. So good afternoon to you all. I hope you guys are doing great today. Please confirm that you can hear me clearly. Hello?
Yes,
Please
sir.
confirm that you can hear me clearly. All
Yes,
right.
sir.
Yes,
We
I
can hear you, sir.
Okay, please also confirm that my screen is clear on your end.
It's clear, sir.
Okay. Good afternoon once again. Um, I know you all know my name. Just for the sake of introduction,
I
one more
was
time.
pointing at this place. I don't mean to unmute.
No, yeah, what do you say? Search the meaning of that. Speaker. Speaker is different from mute. Mute is for a mic. And you go big.
So deliberately, some of us have been made co-host. I would want us to manage this class together. In case some of our colleagues have mistakenly, in quote, turn on their system or they have unmute themselves, please, you should assist to mute them so that there won't be a distraction. I'm sure you all know me, but once again, I'll just say my name one more time. I am Adeleke from the Department of Actuarial Science and Insurance. I'll be taking you Markov chains. About 5 of us are taking this course, quantitative techniques. The course is it's a business administration course, but we have to assist the Department of Biz Admin as they are challenged with staff. So, and I've been asked this time around to take Markov chains. I shared the material earlier, so I hope you all have it. There's a hard copy material that I shared. It's a very good printout. So I will enjoin you guys to make photocopy. It's just about 10 pages material or so. So if you have not got it and you can't find it, your class governor can see me and get the photocopy for scanning. Okay, you can scan and share with others, but if you want the hard copy, you can take mine and then produce yours. So during the course of this lecture, I will be discussing with us the following. I will describe and classify stochastic processes. So I will explain to us what a stochastic process is. I'm sure you will have been hearing of the term stochastic, and then what makes a stochastic process, and then we'll look at the classification of various stochastic processes. So I will also explain to us what is meant by the Markov property. So if you say that a process is Markovian in nature, so what exactly does it mean? So I'll be discussing that with us. And then we will now define Markov chain. So what does Markov property has to do with the Markov chain? How is our Markov chain a stochastic process? We will discuss that. And then we will define some of the terminologies that are commonly used in Markov chains. So after which we will discuss the properties of Markov chains and then show examples. So that will be the summary of how this class will go. At the end of the day, students are expected to understand the concept of stochastic process. We're expected to understand the concept of Markov property. So when you say someone is behaving Markovian, you should understand exactly what it means. And then Markov chain. So you will understand Markov chain, and I expect you to also reduce any practical problem around you to Markov chain if they can be classified as such. So you should be able to apply them in practice. Although we are not trying to make a mathematician out of you, but it is good that you understand some of those concepts, and so that when you encounter them in texts and see how they have applied in the real world, you will appreciate what has been done. So we start by explaining to us what a Markov process, a stochastic process is. So when we say stochastic, we know that our random variable, when we say random variable, it simply means a real valued function defined over a sample space. Let's say that you tossed 2 coins. You know, when you toss 2 coins, 2 fair coins, there are 4 possibilities that you can get. So if you define a function, say y, and that function counts the number of heads that you can get from the throw of the 2 coins, then your y could be 0 when you have no heads, y could be 1 if you have 1 head, 1 tail, and y could be 2 if you have 2 heads. So you can see that y depends on what happened in the sample space. The sample space we are referring to here is a set of all possible outcomes, you know, of that activity of throwing 2 coins together. So the exact outcome cannot be predetermined, but you know all the possibilities. So if you put all those possibilities together in a set, we have what we call the sample space. So if you define a function over that sample space, that function is a random variable. You know, when we perform activities, the activity that we perform can be classified as either stochastic or deterministic. So when we say deterministic, it means that from that activity, you can predetermine the outcome from that activity. But when you cannot predetermine the outcome, that the outcome is purely random, then you say that your activity is stochastic in nature. So which means you cannot predetermine the outcome. So when you have a random variable that you observe at different times, at time 1, you make your observations. At time 2, you make your observations. At time 3, you make your observations. And then if you put all those observations together in a set, all those random variables together in a set, what you have is a stochastic process. So which means the random variable is time dependent. So we define our stochastic process as a model for time dependent random phenomenon. So usually we denote our stochastic process as X subscript T, as we can see on the screen, X subscript T. So that XT is the process. The T there represents the time. So I can have a process at time 1, okay? The process at time 2. So when it's at time 1, it means that our T is equal to 1. When it's at time 2, our T will be equal to 2, and so on. Now, those processes assume values at different times. So you can have, at time 1, the process can take a value maybe 52. The process can be at time 1, maybe if you are classifying your investment as profitable, break even, or loss. So at time 1, your investment can be profitable. At time 2, your investment can be loss. At time 3, your investment can be break even. So you can see that your process takes different value at different time. Now, the value that your process takes is called the state. The value that your process takes is called the state. The time at which the process take that state is simply your time. So you can have x1 equals to 5. That means your process at time 1 is in state 5. So if you say that x3 equals rainy, so if you are dealing with weather situation, then you can say that, oh, the process at time 5 is rainy. So if you are looking at the health of an individual, so we can classify the health of an individual as being healthy, sick, okay, if you're looking at this two-state classification. So we can say that at time 5, this individual is sick. So we write it as x5 equals to sick. So if you are interpreting that in stochastic process balance, you will say the process at time 5 is in state sick. So an individual at time 5 is sick. So the value that the process takes is the state, and then we use the time of the observation. We use it as the subscript. The x there is simply the random variable. It could have been y, it could have been z, it could have been w. All right. So we go back to the screen. So we said a stochastic process is a model for a time-dependent random phenomenon. So it is the collection of random variable xt, one for each time t in some set t. So when you put all the possible sets, all the possible values together, all the possible states, remember I said the value that the process takes is called the state. Okay, so if I put all the possible states together in a set, then I have what we call the state space. The state space. And then if I put all the possible time, if I put them together in a set, then I have what we call the time set. Time set. So we need to understand this concept before we start defining Markov chain. Now let's look at the different classification that we can have. But so I defined all these, the component of stochastic process. Remember, I said the state space is the collection of all possible values that our stochastic process can take, while the time set is the set of the possible time. So we need to understand that as we move on. So now let's look at the possible classification that our stochastic processes can be. There are 5 possibilities that we can have as our stochastic process. 5 possibilities. As we can see on the screen, I'm looking at the different possible ways by which I can combine my time with my state. Meanwhile, I'm open to questions and clarification anytime. All you just need to do is to raise your hand. I'll give you audience. So please, you don't have to wait until the end of the lecture before you ask questions. And also, in the chat area, please kindly type in your department and your name, and your matric number. That will be used as the attendance for the class. Thank you. So we are looking at the classification of the stochastic process. So the classification will be the number of ways that you can combine the time and the state. Now, look at the state. We said our state can be discrete or continuous. The same for the time. The time can be discrete or continuous. From your FBA 220 and FBA 310, we have been told that our data can either be discrete or continuous. When we say discrete, it means that we are dealing with countable, okay? Countable data. So the countable data takes they are from the set of natural numbers, okay? 1, 2, 3, 4, and so on. And continuous data represents measurement, okay? Measurement. They are from the set of real numbers. So they can take any value, okay, from minus infinity to plus infinity. So when we say that our state is discrete, so it simply means that you can count the state, or at any given time, that state can be classified into a definite category. So we can have investment being classified as profitable, break-even, loss. If that is how you have defined the outcome, then it is discrete. You can define the state of any human being as either healthy, sick, or dead. There are definite classifications. So those classifications are discrete. But on the other hand, you will have them as continuous. Okay? So we also have our time too. We know that if you look at time the way it is, 3:25, this exact time, or you can say 1 p.m., but that 1 p.m. is not exactly 1 p.m. It could be 1 p.m., some seconds and so on. time, looking at it physically, they are continuous quantities, okay? But you can discretize it. You can discretize time and say that at the end of each day. So if you now decide to take your observation at the end of the day, or you summarize your findings at the end of the day. So days are discrete. So if we do all the possible combination, so we can have a stochastic process with discrete state space and discrete time set. The state, remember, they are the values, they are the observations that you see, that you got at any given time. Okay, so the discrete state space with discrete time set is one category. You can also have your stochastic process being classified as discrete state space with continuous time set. Discrete state space with continuous time set or continuous time change. You can also have it as continuous state space with discrete time set. Continuous state space with discrete time set. And it's also possible that we have it as continuous state space and continuous time set. The last category that we can have is the mixed one. The mixed processes has for its state a combination of discrete and continuous. Even for the time, a combination of discrete and continuous. That's what makes them the mixed process. Now let's take them one by one and explain the scenario that each of them explain. Now let's look at the case of discrete state space with discrete time set. Discrete state space with discrete time set. Now consider a motor insurance company that reviews its customers yearly. You know, as far as insurance are concerned, claims being made is considered to be loss. So as much as possible, they would want the policy holder to make as less claims as possible. My co-hosts are not doing their job. I don't have to be muting them myself. So please, you should assist to be muting some of our colleagues that their hand are mistakenly on muting. So please, so that we can have a smooth class. Okay, so you consider an insurance company that review the status of their policyholder at the end of the year. So in order to encourage them to be good customers, you know, in order to encourage them not to make claim, because whether they like it or not, premiums will have to be paid because it's compulsory insurance anyway, especially for motor. So they don't have any choice. They will have to pay premium at the beginning of every financial year. So to encourage them not to make claim, the insurance company can decide to issue some level of discount. All right. So that means at the end of the financial or at the end of the policy year, a review will be made, and customers are given 3 different levels of discount. So you have some that are on 0% discount, some are on 25% discount. Others are on 40% discount. So, and it is done in such a way that if you are just entering into the policy, they place you at 0, and then they tell you at the end of that year, if you have not made a claim, we will transit you to 25%. At the end of the second year, if you have not made a claim, we will transit you to 40%. And that you will keep enjoying this 40% discount as long as you are not making claim. So you can see that this is a stochastic process where the states are discrete. You can see what are the states: 0% discount, 25% discount, 40% discount. And then the time set is discrete because the time of review, remember, is at the end of the policy year. So the time will be from the set of natural numbers. So this is a typical example of a stochastic process with discrete state space and discrete time set. Okay, so you could also have other forms. You have a grocery store, and then you want to encourage sales, so you can come up with schemes, okay, that places customer on a different level of discount depending on whether they met some conditions or not. And if the customer status have been reviewed at the end of the year, then it means that the time set is discrete because it's at the end of the year. So to be at the end of year 1, year 2, year 3, and so on. And then the state, which is the discount level that you would place them, is also discrete. So you can there's a lot of activity that you can use the stochastic process with discrete state space and discrete time sets to model. All right. So then let's move to another category that we can have. So look at the typical example of discrete state space with continuous time set. Discrete state space with continuous time set. Now, this is typically being applied, especially with health maintenance organizations, the HMOs. They use this a lot in classifying the subscribers. So a subscriber can be in any of 3 possible states. A subscriber can be healthy, so we use H to denote it. A subscriber can be sick at any given time, or a subscriber can be dead. So those classifications are definite, 3 of them. Those classifications are discrete. They are the state. They are the values that your process can take at any given time. So the states are discrete. Now, what of the time? I'm sure you will agree with me that an individual that can be classified as healthy now can fall sick at any time. You might be healthy in the morning, and then before 12 noon, you are sick. We've had situations where individuals that are healthy in the afternoon suddenly drop dead before dawn. So, and then I'm sure you all heard the news that many Nigerians died during the last football match. So you can see the time of transition is continuous, but the possible state, as we can see, is discrete. So how will you model it? So you model it with a stochastic process with discrete state space, and discrete time set. So let's quickly do a review of what we have done so far. Remember, I started with the explanation of stochastic process. So I told us that the stochastic process is a model for a time-dependent random phenomenon. So, and then we said it is a set of random variable xt, where your xt, where your t represents the time, the t is the subscript, which represents the time. And then the possible values that those xt take, they are called state. So, and that when you put all the possible states together, we have what we call the state space. Also, if you put all the possible time together, you have what we call time set. And that our stochastic process can be classified based on the combination of the state and the time. So we have said that there are 5 possible classifications of our stochastic process. Our stochastic process can be discrete state space with discrete time set. So I've given us an example of that already. You look at the example of the insurance company that is classifying its customer at the end of the financial year or the policy year as being on different policy, different discount level. So the time has been discretized. You know, it is at the end of the year. So it is not taking hourly, secondly, or using minutes. So it's taken at the end of the year. So it could be year 1, year 2, year 3, and so on. So in that wise, the possible times are from the set of natural numbers. So they are discrete. And then the states too, which is the level of discount that the customer enjoy, is also well defined and is discrete. And then we have also taken the example of discrete state space and discrete and continuous time set. So we have the classification that is mostly used in the health insurance sector of the economy. So you can have an individual being classified. That's the HMO. They have enrollees in their system, and those enrollees can be classified at any given time as being healthy, as being sick, or dead. Those are the 3 possible states that they can have. And the time at which people transit from being healthy to sick, and being sick to dead, or being healthy and then suddenly moving to the state of dead, that time is continuous. All right. So in that case, the stochastic process is of discrete state space, but with continuous time set. So now let's look at another example, another classification that we can have. So we can have a stochastic process of continuous state space at discrete time set. Continuous state space and discrete time set. Now let's look at the weather example. So you have the meteorological department of Ministry of Environment taking information about average daily temperature. Okay, average daily temperature. So we all know that temperatures are measured, right? They are measured. We don't count temperature. So of course, the average daily temperature will have to be continuous. So you can have it as maybe 16.05 degrees Celsius, or you can have it in Fahrenheit or whatever. So the state could be, the states are definitely continuous. But because you measure at the end of the day. So which means that you will have it at the end of day 1, at the end of day 2, and so on. So the days have already been discretized. So the time set is from the set of natural numbers. So in that case, the stochastic process there is continuous state space for the temperature and discrete time set for the day, since you are measuring the temperature at the end of the day. So we also have the fourth one, continuous state space and continuous time change. Continuous state space, continuous time change. Look at the exchange rate, for example. Exchange rate to the dollar to naira. So the exchange rate, what you change naira to will be the state, okay? And then the time that it changes, of course, will be the subscript. So we can have it as $1 could be 1,450 naira by 12 noon. And by the time you are at 12:05, the value will be a little bit higher, a little bit lower, and so on. So in that case, you will see that the state, that is the rate of the change now, will be continuous, okay? 1,500 and something 0.52 kobo. It's continuous. They represent measurement, all right? And then the timing too, in this case, the timing have not been discretized. The timing is also continuous. So the exchange rate to a naira is an example of a stochastic process with continuous state space and continuous time set. Now, and then the last one is the mixed process. So when you have a process that the time set is a combination of discrete and continuous, even the possible states too, it's also a combination of a discrete and continuous. In that wise, you will have mixed stochastic processes. So those are the 5 possible classifications that we can have. Now let's look at some terminologies that we will be using in this Markov chain lecture. So the first one is the Markov property. Markov property. Now, a process is said to have a Markov property if the next state that the process will be depends on the current state only, irrespective of what has happened in the past. So whenever you have a process that is memoryless, that doesn't keep memory, that whatever happens next depends on what is happening now and now alone, irrespective of what has happened in the past, that process is said to possess the Markov property. So the Markov property is a memoryless property. It just simply says that, look, what happens next depends on what is happening now. And that is all. So if you have that kind of process, then that is a Markov property. So there are some of us that are finding it difficult to remember things, that their memory doesn't go beyond the immediate past. So what they can remember now depends on the immediate past and not previous historical happenings. So in that way, you can describe them as being the attitude has been Markovian. Okay, so when somebody is being described as Markovian, it simply means that that person has a memory issue. Okay, so what is happening now depends on what has happened in the immediate past or what will happen next depends on what is happening now and now alone, irrespective of what has happened in the past. That is what the Markov property is talking about. So you can see in the screen. So we say that for the Markov property, the behavior of the Markov process depends only on what state it is in and not on its past history. Okay, so it's a manifestation of the memoryless property. So from the underlying assumption of exponential distribution. So once again, I am open to questions, observations, clarification, and comments. So I don't want it to be a one-way thing. You guys are not listening to inaugural lecture. So you are free to ask questions if you have any. All right. So, but I try as much as possible to make sure that my teaching is simplified. So another term that we will be using is sojourn time. So the sojourn simply means the time spent in a given state. Okay. So if a customer, in the case of the insurance company that is giving discount, if a customer stays on the 0% level for 5 years, you know what it means? It means that that customer is not enjoying any discount level. It's also, it means that the customer is a very bad driver because it's always making claims. So when you have that person sitting on that classification for a very long time, let's say 5 years, then we can say that the sojourn time is 5. All right, it's 5. So and then as we are moving on, we have said that the sojourn time, that is the time that that person stays on that on each of the states, is exponentially distributed. Well, don't let me be too technical on this. Exponential distribution is one of the parametric distribution that is usually used to model data. Okay, so when you plot it, it looks you see that it's used to model data that degenerate very fast, or data that increase at a very fast rate. Okay, so exponential distribution, they are very good in modeling such. All right. So another term that we'll be using, we have the transition, before transition probability. You see, when you move from one state to another, like in the example of the discount level, a customer is on 0% discount this year, and then next year, because of its good behavior, that customer has been upgraded to 25%. You don't say that customer move. We use the word transit. All right. So movement of the process from one state to another is transition. So we say that a process transits from a state to another state. So transition is what we used. So the rate of the transition is called the transition probability. All right. So that gives you the possibility that a process that is currently on a particular state will be in another state at the next period. So that is the transition probabilities. So when we put all the possible probabilities together, the possible probabilities are usually in a matrix form. as we will see moving forward. So when you put all the probabilities together in the matrix form, we have what we call the transition matrix. Transition matrix. So we'll make use of them as we move on. So let's just do a recap again of what we have done, and so that we will maximize benefits from the lecture. So I started by explaining to us what a stochastic process is. So I said a stochastic process is a collection of random variables at different time. Then, and I said that the value that the random variable takes is called the state. Okay, and then the time at which the random variable takes those states, we use, they are put as the subscript. So we can have x1, x2, x3, and so on. So at x1, we can have x1 equals to 8, x2 equals to 10. What it means when you say x1 equals to 8 is that the process at time 1 is in state 8. So when you have x2 equals to 10, it simply means that the process at time 2 is equal to 10. So the value that the process takes is the state. So when you put all the possible states together in a set, we have what we call the state space. And then when you put all the possible time together, we have what we call the time set. So we use this to classify our stochastic process. And we say that there are 5 possible classifications that our stochastic process can be. That our stochastic process can be a discrete state space with discrete time set. It can be discrete state space, continuous time set. You can have continuous time set, discrete state space, continuous time set, continuous state space, and then we can also have the mixed process where the state can take both continuous and discrete values, and also this the time too can be both continuous and discrete. So we had example to illustrate each of the possible classification. And then we've also done Markov property. I explained to us what the Markov property is, that a stochastic process is said to have the Markov property if the next state of the process depends on the current state only, irrespective of the historical states. So if you have that kind of process, then that process possesses the Markov property. So the Markov property simply demonstrates that the process is a memoryless process, and that the behavior of the process is such that what happens next depends on what is happening currently now, and not what has happened in the past. So, and then I also explain some terminology that we'll be using, terminology such as Son-John time, exponential distribution, what a transition is, what is transition rate or transition probability. And then I also mentioned the transition matrix. So so that's what we have done so far. So let's now move on to Markov chains. Markov chains. So do we have questions? I want to hear from you. Do you have any question? You're all quiet. Okay, so let me assume that there's 100% understanding, or you are just waiting to listen again to the recordings. All right, so let's look at what Markov chains are. Remember, we have discussed the Markov property. that a stochastic process possesses the Markov property if the previous state depends on the current state only, irrespective of the past. So if you have any process, okay, any stochastic process that that has the Markov property, and the state too, the time set, sorry, and the state is also discrete. I'll take it again. Two conditions. If you have a stochastic process whose property, okay, is Markovian, one, and two, whose possible states are discrete. If you have those two conditions holding, then the process is not just a stochastic process, it's a Markov chain. So a Markov chain has the Markov property, and the state is discrete. It is not all stochastic process that has the Markov property. There are stochastic process that the next state depends on accumulation of all previous states. That, look, what happens next depends on all events, all activities in the past. So yes, it's a stochastic process, but it doesn't have the Markov property. So that cannot be a Markov chain. Okay, a Markov chain, one, must possess the Markov property, and then two, the states are discrete in nature. So that's what makes a Markov chain. Now let's look at the screen. Let's look at the screen. Please just open your mind. This mathematics is not too complex for you to understand. So we said a stochastic process Xn is called a Markov chain if you can see the probability that Xn plus 1. It simply means that the probability that the process at time n plus 1 would be in state J, given that at time 0 it is in state K naught, and so on. At time n minus 1 is in state Kn minus 1, and at time Kn is in state I. If it is equal to the probability that the process at time n plus 1 will be in state J, given that at time n is in state I. So you can see it doesn't put into consideration what happens in x naught at time naught, what happens in x minus 1 at time n minus 1. It doesn't put into consideration of all that. What it puts into consideration is the present. You know, the present is xn. So the probability that the process at the next stage will be in state J, given that all previous states are stated and that the present state is in state I, it simply equals probability that the process in the next period will be in state J, given that the present period is in state I. Once that condition holds, and the states too are discrete, then what you have is a Markov chain. All right, it's a Markov chain. Just historically, the credit has to be given to Markov. Markov lived in 1856 to 1922. So as part of his PhD thesis, he published this, as a way to explain some activities. So Markov actually introduced the Markov chain. So it was named after Andrei Markov, the Russian mathematician. All right, so let's look at the possible Markov chain that we can have. Remember now that a Markov chain is a stochastic process that has the Markov property and also the state is discrete. All right, so we can have two types of Markov chain. So we have the discrete time Markov chain, DTMC, and also continuous time Markov chain, CTMC. MC there is the Markov chain. Okay, T is the time, and then C is continuous, D is discrete. So remember, the state is already known. The state is discrete, and it is memoryless. All right, that's what makes it a Markov chain. So, but the Markov chain can be discrete time Markov chain and continuous time Markov chain. So, now let's look at transition probabilities and the properties of transition probabilities. All right, so now when you put all the probabilities together in a set, we have the transition probability. I've explained to us what transition is. Transition is the process being moving from one state to another. That movement is called transition. Okay, so if your process is currently at state 1 and then it progresses into state 2, so you don't say it progresses, you don't say, you simply say the process transits to state 2. So our co-hosts, you guys are not doing your job. You know, some of us will have our hands move to the unmute button, and then some background noise will start coming up. So please should assist me to help manage the class so that we can have smooth lecture. So now look at the subscript. Okay, are we seen the subscript? 0, 0, 0, 1, 0, 2, 1, 0, 1, 1, 1, 2, 2, 0. 2, 0, 2, 1, 2, 2. Now, what do they mean? You see, the P there is the probability of transition. All right. So when you say 0, 1, now look at the states. The states, there are 3 of them: 0, 1, 2. And that is why the matrix is a 3 by 3 matrix. So when you are labeling them downward, the label should have been 0 here, 1 here, and then 2 there. And at the column 2, you should have 0, 1, 2. So when you say 0, 0, that means the row is 0, the column is 0, right? When you say 0, 1, the row is 0, the column is 1. When you say 0, 2, the row is 0, the column is 2. Now, what does it mean? It means that the probability that the process will transit from 0 to 0, the probability of the process remaining at state 0. That's what that P00 means. Probability of the process remaining. You know, if it remains at state 0, it simply means that it transits back to 0. All right, so that's what it means. Probability of the process transiting from state 0 back to state 0. So if it is 0, 1, it means that the process transiting, the probability of the process transiting from state 0 to state 1. If it is 2, the probability, that's 0, 2, it means it's probability of transiting from state 0 to state 2. So the 0 there representing where the process is transiting from. The 2 there representing where the process is transiting to. Okay, so if you have it as 3, 1, it means that the process is transiting from state 3 to state 1. So that's how it is written. All right. So if I'm to interpret what I've written here at the top, at the very first line, it simply means the probability that the process at time n-1 will be in state J, given that at time n is in state I. So if we are starting afresh from 0, we are moving to 1, you can interpret it. Look at what I have here. The probability that the process at time 1 will be in state J, given that as time 0 is in state I. All right. So we can write it as Pij here. The I and J, remember, they represent the state. I is where you are transiting from. J is where you are transiting to. And that explains what I was I've explained what we have in the transition matrix of P00, P01, and so on. Now let's look at this example. So deliberately, I've given the source of the material. So you can follow that link and get more information. So that's where I got it from. So you can always do a follow-up reading. So we have a 3-state model. So the states, they are 1, 2, and 3. And then the probability of transiting from each of the states have been compiled, and then you have a 3x3 matrix. So you can also see the graph. The graph of transition have also been given. So look at 0.65 now. It's the probability that the process transits to itself. And you can see, you look at the arrow, you see, it is coming from 1 and then ended up going back to 1. That's what we mean by transiting back to 1. Okay, so in that case, if you want to write it, you write it as P11, P11. Now look at the top heading and then look at the row heading. So you can see the S1, S2, S3 there. S1, S2, S3 there at the top row too. So usually we don't put the classification there, but just for the sake of teaching, those classifications have been put 1, 2, 3, 1, 2, 3. Those are the states that the process can be, all right, at any given time. So this is how you can represent your transition matrix. Can represent it in a graph, as shown. All right. So now let's look at different stochastic process that we can have. So this is a 2-state model. You can see 2-state model. This is for studying weather. So the weather can be classified, in this case, the weather can be classified as sunny or cloudy. Now, the probability has been put there. That probability can also be referred to as the matrix generator. Okay, it generates the probability of transition. So from records, all right, they have already identified the probability that when a state is sunny now, what's the probability that in the next day it will be followed by a sunny day? So 0.8 there simply means that 8% of the time, all right, a sunny day is followed by a sunny day. All right, so that's why it is not written. We didn't write it. It should have been state 1, state 2. Then at the top 2, you will have it as state 1, state 2. So that means 0.8 is P11. That means the probability that a state will transit from 1 to 1. What is 1 there? Sunny. All right. So which simply means that the probability that a sunny day will be followed by another sunny day. Okay. Then the 0.2 there is P12. That means a cloudy day following a sunny day. All right. And then 0.6 there simply means a cloudy day. Okay. So this is P21. So it simply means that the probability that a cloudy day will be followed by a sunny day. And then 0.04, 0.4 simply means that the probability that a cloudy day will follow a cloudy day. P22. 2 is cloudy, 2 is cloudy. Okay, so and then you can see the graph, how it is transiting from one state to another and so on. So you can see that you can classify so many of our processes as long as you can define the state clearly, and as long as you can define the time clearly, you can classify our stochastic process accordingly. So we have many of them. Some of us are just playing around with our fingers. So please be careful so that we don't disrupt the class, right? But you can unmute and then ask questions. That is allowed. Okay, so now let's move on. Let's take another. Let's look at special cases of Markov chains, right? So far you will agree with me that the Markov chains is a very, very important topic for you guys to learn. It's very, very useful. It is not all the time that you want to make projections and then you start plotting and then you see some charts and then you start saying, oh, this is rising, it's falling, and so on. You could have activities that are based on classification. How will you make projection? Okay, activities that are based on classification. Oh, making profit, not making profit. Oh, our customers, they are enjoying this level of discount, that level of discount, and so on. And then you want to know how many of your customers is likely to be enjoying 50% discount. How many will be likely to be enjoying 80% discount, and so on. How will you do it? You can't just be relying on mathematical modeling, just putting for formula and so on. So our stochastic process comes into play. And that's why the Markov chain is very, very important, right? So if you have a process that you can classify into definite states, being discrete, and that the process has a Markovian property, that means what happens next depends on what is happening now alone, then you use Markov chain to model it. Okay, so what does the Markov chain says? You just define your state clearly, and then what are the probability of states? What are the probability that your process will be in each of the states? And then you put them in a matrix form. How will you get the probability? You need to observe activities in the past. Go into your historical activity. So if you are dealing with a weather scenario, so all you just need to do is to watch out for maybe rainy days, and then you look at how many times have you observed a rainy day being followed by a rainy day. You count, and then you put it in the cell. How many times have you observed a rainy day being followed by a cloudy day? You count, you put it in the cell. And then you go back again. How many times have you observed a cloudy day followed by a rainy day? You put it in another cell. And then finally, how many times Have you observed a cloudy day being followed by a cloudy day? So you have the frequencies. You add up each row, and then you divide the cells by the addition of the rows. That is the probability. That's how it is done. And then you now use it to make your projection, as I will demonstrate later on. So these are the classification of stochastic, of Markov chain. So our Markov chain can be regular. Our Markov chain can be absorbing. Our Markov chain can be reducible, can be ergodic, can be stationary. Now let us just look at the case of regular Markov chain. So if the probabilities in the entries remains positive, okay, for all the steps, then that Markov chain is regular. I'll take it again. Whenever you have the probability, of course, we all know that probability has to be positive, but it has to be strictly greater than 0. Okay, not equals to 0. So you can't have in the cell, in the matrix, one of the cells being 0. No. So they have to be greater than 0. So if you have that kind of matrix, as the number of steps increases, then that matrix or that Markov chain is a regular one. Then absorbing Markov chain. Absorbing Markov chain. If you have a situation in which whenever you transit to a state, you can never move out of that state, then that state is an absorbing state. Then that means that Markov chain that matrix represents is an absorbing Markov chain. Look at the case of a two-state Markov chain, with one of the states being alive and then one state being dead. You know, if you do the transition matrix, you will notice that once a person has moved into the state of dead, that individual can no longer transit out of that state. It will remain in that state forever. So the probability of transiting back into that state is absolute. It is 1. So if the state of death is 1, is 2, that means you will have P22 will be equals to 1. That is probability that the individual being in state 2 will transit back to state 2 is 1. So you cannot move away from it. So the absorbing state is a state where the process gets into and never move out. So if you have the case of alive and dead scenario, once person moved into the state of death, that person had moved into an absorbing state. It will never move out of that state. So you can have several scenarios. Now let's look at the example of each of them. Remember, I talked about the regular, and I talked about that. So you can see the original transition probability. So you can see that as you move the steps here simply means raising the power, okay? You see that when you raise the power to 2 at 2 steps, you can see that all the cells, all of them, they are greater than 0. So in this case, the Markov chain is regular. The Markov chain is regular. So I can use this to assess you in the test or in the exam. I'll give you different scenario, A, B, C, D, and then I ask you which one of these is depicts a regular Markov chain. Okay, if the initial state have been, maybe I'll give you the matrix. So you should know. And then look at this the second Markov chain. Look at transition matrix. Have you seen transition matrix? You see that B equals, and then you have some zeros there. But by the time you move to the second step, some zeros are still there. You move to the third step, zeros are still there. Fourth step, zeros are still there. So in that case, that Markov chain is irregular. It is not regular. All right. So, so example of the adsorbing state. Now look at it. Look at 2, 2. The probability of 2, 2 equals 1. That means you transit back to 2, and so it's absolute. So once you move into that state, you can't move out of it. All right. So that's why it's 1 there. So the properties, the desirable properties of desirable property of Markov chains. The first property is irreducibility. It is desirable that every state should be able to be reached from every other state. So you should be able to move from 0% discount to 25% discount. You should be able to move from 0% discount to 25, 0% to 35, 35 to 25, and so on. So when all the states are reachable, okay, from every other state, then the Markov chain will be referred to as irreducible. Okay, irreducible. And then the Markov chain can be ergodic. So ergodicity is also another important property that is desirable. It is not that you must have it, but it is desirable that when you have a process, when you have the Markov chain, all the units should be able to reach every other unit. So that's the irreducibility. And then the ergodic property simply means that when you transit away from a state, you should be able to transit back to that state in the future. Okay, not that when you transit away, you cannot come back. So so it should be able to transit back into that state, but not necessarily at a regular time interval. So that's why we said that a Markov chain is ergodic if it is irreducible. Irreducibility means that every state can be reached from every other state. If it is aperiodic, that means the time of return to a particular state is not fixed. Okay, not that we say every 2 years it has to be coming back to a particular state. No, so the time of return is aperiodic, and also it has a positive recurrent. That means when you leave a state, it's possible that you come back to that state in the future. And then finally, stationarity is also important. A Markov chain should be it should be stationary. All right. When we say stationary, it means that the joint distribution of the random variable does not depend on time. All right. So it is constant over time. So that is very important. So there are several scenarios, that one can use to that you can model using the Markov chain, as I have stated here. Okay, so there are so many of them that you can use the Markov chain to analyze. All right, so So I'm sure you can read this one on your own. These are just ways of telling you how useful the Markov chain can be in different areas of applications. Now let's move to the end step probabilities. So what do you do with the transition matrix after you have them well documented? So the end step will be used for projection. So if you want to say, for example, you're asking a question in 2 years' time, what's the possibility that a life that is currently or a process that is currently in state 1 will be in state 2? What's the probability that a process that is currently in state 2 will remain in state 2 after 2 years? So how do you work with the years here? You will just be raising your probability. So if you say after 2 years, that is 2 steps. So you have to raise your P to power of 2. So if you say after 3 years, you raise your P to power of 3. After 5 years, you raise your P to power of 5. Raising your P to power of 5 simply means that you'll be multiplying the matrix by itself 5 times. Okay? And then the cells there will now be used to answer those questions. That's how they are used for projections. All right? So if it is possible that you keep multiplying the matrices by itself, and then you get to a state where the probability suddenly becomes the same as you multiply. That means you notice that your probability at time 10 is the same as that of time 11. Probability at time 11 is the same as that of time 12, and so on. So if after a step you discover that the probability remains constant, if it is possible for you to reach that state, then that state is called the steady state or the limiting state. That means after a while, the Markov chain becomes stationary. Now let's take an example. Still on the insurance company classification. Every customer at the end of the policy year will be classified as being on 0%, 25%, and 40%. So the question now is, out of 1 million customers, how many do we expect that in any year, how many do we expect to be in 0% level? How many do we expect to be in 25% level and 40% level? So to answer that question, you need to ask yourself whether the Markov chain will become stable over time. So which means you keep multiplying the probability by itself until it becomes stable. Or using this mathematical form, you are saying that, look, you are looking for a pi such that when you use that pi to multiply the probability, you get back your pi. If you can attain that state, then the Markov chain is stationary. Now, the probability that you get, you will have 3 sets of probabilities. You use your 1 million to now multiply. You know, that gives you the expected number. So in the long run, you'll be able to know, you'll be able to estimate the number of customers that are expected to be enjoying 0% discount. The number that is expected to be enjoying 25% discount. The number that is expected to be enjoying 40% discount. That's how to apply it. So that stability will be able to allow you to do the expectation computation. But if that stability cannot be reached, it will be difficult to answer that question, because it means that from time to time, that number will be changing. So you will not be able to answer that question. Oh, at any given year, how many do we expect to be? Okay, so that's what the stability would have brought for you. So if you look at the solution of that question of whether you can get a pi, such that when you use the pi to multiply your probability, it will still give you your pi. So you can see that that has been solved here. Okay, and then we got the possible pi's are 0.474, 0.321, and 0.205. Okay, so that's the implication. All right. So I think that's what I have for you. There are ways that you can implement some of this in Excel. That is outside the scope of what I'm supposed to teach you. But I would advise you to have a look at these questions. Some of them can be useful, especially when we know that our test is coming up in 2 weeks' time. A Google form will be presented to you guys to answer your question, maybe within a given time limit. So some of these questions can come handy. Just have a look at them, and you never can tell. So, ladies and gentlemen, that is all that I have for you. Please compliment this slide with the documents that I said I've made available earlier. If you don't have it, you can send your class governor to me. I will release it. The class governor can scan and send to everyone, so that nobody will be disadvantaged in any way. So I'm open to questions if there are any, and if there are none, I will bring the class to a close. Please try as much as possible to sign the attendance. The attendance will be collected on the charts. Write your name, your department, and matric number. So I'm open to questions if there are any. Questions, please. Okay, if there are no questions, I think we should bring the class to a close. I will try as much as possible to compile about 30 or 40 questions for you. I will share them. I will share the link so you guys can have a look at it. They can be useful. So, on that note, I want to tell us that you guys should have a nice weekend. So I'll see you some other time. Bye-bye.
Thank you, sir.
Bye-bye, sir. Thank you very much, sir.
Bye-bye, sir.
Sir. Bye.
Dragon Street.